Hi, this is Chendi Xue. This is a demo presentation for our proposed talk of building billion-scale social media pipeline with Spark 80 times faster. Social media data is increasing explosively. We use two public datasets as example. Critile has 671 billion records with 40 features. And Rex's Challenge 2021 has 1 billion records containing Twitter text, date time, URL, and the relationship with user account. To do feature engineering and train with such large scale data became a challenging problem. Many data scientists are more familiar with pandas or NumPy. It may be a little difficult for them to understand Spark. But if we try to solve this billion-scale problem with pandas or NumPy, it's very easy for us to observe an OOM problem or process hanging there. If we are trying to use NumPy, simply transformations here, it will be extremely slow to take a couple days to complete. So we are now influencing our customers, stakeholders to use Spark, trying to solve the problem of them to understanding the Spark memory tuning, parallelism, and the disk shuffle spilling mechanism. That is why we are building our end-to-end pipeline for billion scale and for them to easily to use that. In this page, I want to explain why pandas or NumPy cannot handle large-scale feature engineering. I use two examples here. One is Categorify and one is target encoding. Categorify is convert string to an ID. So in our example, there is 4 keys in the dictionary extract from the original data, which are apple, banana, Canon, and diploma. So we only need to apply this global dictionary back to the original data. That is how Categorify are implemented. And for test data, there may be some keys never shown in the train data. We will apply a new key to it. For target encoding, it is quite similar with Categorify, but with a different way to generate the ID. In target encoding, the ID is not in sequence, but using the key connect with the final label to it. For example, you can see there are 4 apple here, but with 3 positive label and 1 negative label. That is why the target encoding is 3 out of 4, which is 0.75. And then we apply this dictionary back to original data, and we get the target encoding of each key. For test data, the string is never shown before. We will use the average target encoding applied to this. So there is a problem about the data is billion scale. We think that the unique key of this data set is 1 to 5%, which still means 10 to 15 million keys in this data set. Pandas use factorize method to doing the Categorify. And the factorize is actually store the dictionary in the data type. So there is not possible to store a 15 million dictionary in the data type. And another solution is to use dictionary in Python. But Python dictionary is based on hash map, which means there will be a data argument to original size of the dictionary. And then so we cannot to store a 15 million key dictionary and apply to original data. So the worst but the workable solution is to use NumPy memory map solution, but it will be extremely slow. So we believe when dictionary is that large, we should avoid of using a unified dictionary and broadcasting to original data. The perfect solution is to using Spark partitioning join, which I will explain in the next page. Since this is a demo presentation, I will only talk about the solution of using adaptive memory strategy to resolve the categorify problem. In our pipeline, we will fetch the system information of how many memory and shuffle disk capacity we can use, and we will use this information along with the actual dictionary size to make the decision of which join strategy to use. Be mentioned here is that we can categorize multiple features at once because of Spark has a whole state code gen mechanism, so we can combine different work and process at once. For columns, dictionary is too large, we will fall back to use partitioning join here. And if the categorify is not only to convert a string to ID, but requires a split or some additional filtering, we may either try to use pandas UDF or transformation before the joining. By this adaptive strategy, we use the Cretile dataset as an example. The original Facebook release NumPy script took about 5 days to complete or 6.71 billion records transformation, and then now it took about 1.5 hours using Spark. And the results is exactly same with Facebook process 1. At the last page, how the pipeline mapping to Spark looks like. We will do feature transformation using pandas UDF, meaning that data scientists' pandas codes can be easily migrated to this stage. And then we make categorify and target encoding as the second and the third stage. For each stage, since Spark is using lazy execution strategy, we will use RDD cache or save to Packet here to trigger the actual RDD computation, especially for incremental of the dictionary. And for the last stage, we will feed feature engineering, transform the data to XGBoost on Spark training or deep learning on Ray training. Okay, thanks for watching this demo presentation.